Everyone, welcome back. Today I'm going to present to you the full content of Further Mechanics 9231. Right, now we're going to start off with the first topic, momentum. Let's get started. Alright, welcome back. Now we're going to start off with the first topic of Further Mechanics 9231. Let's go through the objective of this topic here. Now, the topic name is momentum. Now, this is a very important topic to go through because in order to study further maths, you need to keep your momentum until the very end, right? Now, the first part of the objective is we are going to revisit or recall and use the definitions of impulse of a constant force and relate the impulse acting on a particle to the change of its momentum here. So it's kind of revisit from what you have studied from your AS. All right. Secondly, we're going to present to you a new topic that has not been taught in A-level mathematics, but you're going to learn that in further maths 9231 here. So we're going to go through what is known as Newton restitution's law, or sometimes it is known as Newton's experimental law. And then what does it mean by coefficients of restitutions, which usually has a domain lying between 0 and 1. All right. And then lastly, we will look at two special cases whereby in both coefficients or restitutions e equals 0 and coefficient of restitutions e equal to 1 that represent both the perfectly elastic collisions and then perfectly inelastic collision. All right. And then lastly, we're going to apply the conservations of momentum and both the Newton's restitutions law to solve any mechanics problem that involve direct or oblique impact um, of two smooth spheres or the direct or oblique impact of a smooth sphere with a fixed surface itself. All right. Now these are the three main objectives that we're going to achieve. All right. Now for today, I will go through the first two objectives by providing you with an example to follow up with the applications of those two objectives here. Okay, first of all, let's look at what is known as momentum, and then is there any other physical quantity related to momentum itself? Okay, let's look at this. Momentum. That's the first one. Now, other than momentum, we also have to revisit or recap what is known as impulse and conservation of momentum in this case. Right? Now, before we go into more in-depth, we're going to look at one simulation here. Okay. Now, you can see that I'm trying to illustrate to you what is the relationship between momentum and impulse in this case. Now, for this example here, we are looking at a particle with a mass m. This particle is particle P. Um, Before this, this particle was moving at a constant speed u1. All right. Now, next, um, I'm going to show you what happens if there's an external force acting on the particle itself. All right, let's look at this. Right, moving at a constant speed u, and then suddenly it was acted by this external force F here. Let's look at what would happen next then. Of course, you would anticipate that the speed would change, all right, it would increase in speed, all right? So there will be a change in velocity. Even though we are looking at the speed is acting in the same direction, so you can actually mention that this is a change in velocity because the speed has already increased due to the external force exerted on the particle itself. All right, now let me see whether it works or not. All right, just let me show you one more time. All right, exerted by a force, there'll be a change in velocity here. All right, okay. Just let me rewind a bit so that you can, let me show you step by step what's going on. Okay, okay. Now, before the particle was acted by external force, this particle has what we known as the momentum. All right, momentum. Briefly, momentum, just to revisit, I'm going to write down here momentum. All right, momentum, as you know, is represented as the product of the mass of the object itself, by the velocity of the object. In this case, we are looking at the velocity u. Okay, and then don't forget, this momentum is a vector quantity. So sometimes you can label that as vector, whereby the velocity itself is also a vector quantity, and then whereby the mass is a vector quantity. Okay, now next, once it is acted by the force itself, okay, once it is acted by the force, there will be a change in velocity. Okay, now from the definitions of Newton's second law, we know that the resultant force is defined as a rate of change in momentum, a rate of change in momentum itself. So before that, I'm going to write down the change in momentum. So change in momentum. Okay, so we have a change in momentum, which is mass multiplied by v. This one will be the final velocity from this point of view, and then you have the initial velocity here. Right, now that will be our change in momentum, or sometime shorthand version, you can actually write this as change in velocity in general. And then Newton's second law states that the rate of change in momentum is defined as the resultant force. So don't forget, this is called the resultant force. It's a rate of change in momentum. So this is rate. Oops, I think I wrote it down wrongly. Hold on, just let me change the labeling. I forgot my m, so I'm supposed to write down mass multiplied by the change in velocity. So Newton's second law states that resultant force is defined as rate of change in momentum. So that is rate of change in momentum. Okay, and then there you have it, right? Or sometime you can also write it down in the form of dv dt in this case. So sometimes you can also write down as Newton's second law is defined as a rate of change in momentum in this form, dv dt. Okay, and then there you have it from here. Okay, now on top of that, on top of momentum, change in momentum, I'm going to show you the next quantity, which is known as the impulse itself. Right, now the impulse itself, okay, can be written as, now I'm going to write it down in the simplest form here. You will notice that F is actually equal to mass dv dt. Right, so from here we notice that we can rewrite in this form. Okay. And then of course, lastly, you can take the antiderivative by integrating both sides here. All right. Now we can start off by looking at time t equals 0. At time t equal to 0, the speed will be, or the velocity is u. At time t equal to t itself, the speed will be a v itself. So from here, we will obtain another quantity which is known as this, multiplied by a t is equal to m v minus mu here. Right. Now, change in momentum is also given by the product of force multiplied with the duration of time. And then there's a special quantity given to this particular calculation. This is known as, it's known as change in momentum. It's also known as impulse. So we'll write down here, impulse is defined as, usually they use J or I, is a vector quantity, is defined as the product of force with time, or you can actually define as rate of change, oops, sorry, change in momentum, not rate of change. So impulse is product of force and time, and it is also defined as change in momentum here, right? So it's a little bit revisit on momentum, a bit of revisit on the calculus itself, and then make sure you understand clearly the definitions of momentum, change in momentum, and then lastly, impulse as defined as the change in momentum, right? Now all these are vector quantity, right? Right, as of the summary of what I have just explained, I'm going to write down the formal definitions and all the equations involved. Now, the first one, the definitions of momentum, usually is given as a vector quantity. Now, in the exam, you don't really need to put the arrow on top. If you knew the direction itself, you don't really need to put that vector. But most of the time, I put the vector just to remind myself in the event in the future you are dealing with momentum in three-dimensional space. This is where the vector two become very important, right? Now, it is defined as the products of mass and its velocity. Bear in mind, it's velocity, not speed. This is a vector quantity. It has both a magnitude. The magnitude is given by the multiplications of the mass and its speed, and then the direction is given by the unit vector of the velocity itself. Okay, so its direction is indicated by the vector. It could be two or three or higher dimension. Right. All right. And then in order to indicate its directions of momentum, you can either use a vector, you can use vector to represent the directions, or you can use a simple sign, positive or negative, just to signify whether it's moving in the positive directions of x-axis or is in the negative directions of the x-axis or vice versa in the y-axis, right? Now you can always use a standard symbol, standard sign in this case. So positive is moving to the right, and then moving vertically upward. Down is considered as negative, left is considered as a negative here, right? All right, now next we also have impulse. Yeah, impulse. Here I'm going to show you impulse first before we visit what is conservations of momentum. Okay, impulse itself, definition. Momentum is a product of mass and velocity. Based on the Newton's second law, we start to derive the impulse from Newton's second law. Um, Resultant force is defined as rates of change in momentum, can be written as dp dt or m dv dt in this case. Now next, impulse is defined as change in momentum. you can I have already shown you how to actually derive that. So the symbol that we always use to represent impulse is either I or J in this case. Now you can use any symbol that fancy you. You don't really need to define it as a vector itself in this case, if the dimension is just 2 dimensions or less. All right. Now I hope that is clear. Right, here I'm going to present to you how to actually apply impulse and simple calculations on momentum. All right. Now this is our first example. Right. Now we have a particle of mass 4 kg is traveling in a straight line on a smooth horizontal surface. The particle is moving at a constant velocity of 3 meter per second when a force of magnitude 5 Newton is applied for short durations of 0.4 seconds. Now, if you read through this paragraph here, you notice that they mention moving at a constant velocity of 3. Constant velocity of 3 meter per second is considered as moving to the right. Right? That's our basic convention. The question here is we need to find the impulse applied to the particle and the velocity after 0.4 second, because once the force is applied onto the particle itself, there will be a change in velocity, or in this case change in momentum then. Now the particle does not change direction during its motion. Alright. Now just to show you how it look like, so in this case is more or less the same diagram that we are looking at. Okay, so you can see that moving at the 3 meter per second, acted by an external force, and then there's a change in velocity. Okay, so let's look at how to work with this. Okay, so in this case we have if you want to make your working easier, you can always write down all the symbol based on the context that is given to you here. All right. So we have the force. So you can write it down as force, 5 Newton. Now, if you want to represent this force in the vector form, um, okay, by all means you can go ahead. But anyway, we are only looking at in one direction, so you can actually write this without indicating the using the vector notation, right? And then our initial velocity was u equal to 3 meter per second. Okay, and then the durations of time is 0.4 second. All right. And then what do we need to find here is we need to find the impulse. That's the first one. And then finally we need to find out uh, what would be the increase in its velocity. Okay, now that's what we have at this point of time. Yeah, I think I'm also miss out the other information. It has a mass of 4 kg, so I could have written this one down also. Right, now we have captured all the informations required, and then we sort of have a visual understanding how the motion look like from our perspective here. Okay, now we are ready to find its impulse. So impulse is defined as change in momentum. So change in momentum, or here I omit the vector notation. It can be given as change in momentum or product of force and its duration of time. Right. You can see that in all my working, I try to ignore the vector notation here because I noticed that this is just a straight line linear motions, just in one direction. So I don't really need to pay too much attention to the structure of vector in this case. Right. Now from this formula itself, I found that in order to find impulse, it's easier to use the first part, right? So therefore, the impulse is given by we have a force. Make sure the time is in second. Every second count in the exam. So therefore, you have two impulse has a unit of Newton second. Yeah, and then there you have it. Or some of you uh, may want to recap another units for impulse, the SI unit for those students who are uh, taking physics subject. You can also use both of these units. Right? So once we have found the impulse, we can make use of the impulse to find out what is the change in velocity. So here we know that change in momentum is the same as its impulse in this case, which is equal to 2. We have the mass as 4. All right, and then there you have it. Therefore, you get 3.5 meter per second. All right, so from here we found that after the force has been acted on the particle gain kinetic energy. So it speed up to 3.5 meter per second here. All right, now I hope this example give you a good recap of what you have learned so far. All right, let's look at our second example here. We have a particle of mass 10 kg travels in a straight line again. When the particle is traveling with velocity of 12 meter per second, an external force of magnitude 18 newtons is applied to the particle for 12 seconds here. Given that the particle direction is reverse, find its velocity of the particle after 12 seconds. All right, now let's get a visual look at how the motion look like before we try to attempt to apply the formula itself. So let's look at this. Right, so it's moving at a constant speed, 12 meter per second, acted by the force, and then therefore change direction. You will notice that the directions of the force is against the initial motion of the object. That may be one of the reasons why the particle changes direction after it has been acted upon by the force F here. All right, so that is all the informations we have as usual. For a good practice, okay, we always write down all the informations and then use the appropriate symbol. In this case, we have a mass 10 kg, and then we have the initial velocity. Initial velocity was this direction. Okay, so 12 meter per second. And then its final velocity, we have no idea. Okay, the time given, yes, we do know that the force is applied for a short durations of 12 seconds. The force involved in this case is, I just write down here, the force is 18 Newton here. All right, and then generally we are almost done. Okay, now before we get started with any question involve vector quantity, it's always good to assign or use a standard reference direction. So here we assume that any directions to the right is considered as positive. We use it this way. So any directions in that standard reference is considered as positive. All right. Now we're going to come back to the formula that we can actually apply here. All right. So that gives us the idea of impulse. As long as there's an impact in this case, you can always think of a formula that involves impulse here. So we have the force, time, all right, okay. So we have the force here. All right, now because force is acting in the opposite directions of what we have actually assigned. So therefore, we're going to write down our force as negative 18 then. Time is a scalar, so no direction is served. I just have to write down as 12. Mass is 10. Uh, V. V is the one that I'm interested to find. Now, of course, I knew that V is in the opposite directions, definitely. Right? So you might want to put a negative sign here, for instance, because it's acting in the opposite direction. And then initial velocity was U, was 12. Mhm. And then do check if you have all the informations here. Yes, we are quite happy with that. And then do a bit of simplifications here. We will get 10 V plus 12 is equal to 18 by 12 here. All right. So I hope that is clear at this point. Okay. Do check, especially the sign. So I'm going to pause here for a while for you to observe how I have used my standard direction as my reference to all the vector quantity. Any vector quantity, you have to take into account the positive or negative direction. Because here we are not using the vector notation, so the positive and negative become very important in this case. Right? Okay. So from here onwards, we will get in this case, that will be a B plus. You divide by 10, you will get 21.6 here. Therefore, in this case, it will be like 9.6. Yes, correct. All right, 9.6 meter per second here. All right, just let me double check with my calculator in case I get it wrong. Okay, so therefore we found that the velocity of the particle after 12 seconds is given as 9.6. Of course, if you want to write the appropriate velocity here, you can write it down as a negative direction if you want to indicate the if you want to use a sign to indicate its direction. Yeah, but the magnitude of the velocity of the particle after 12 seconds would be 9.6 meter per second. All right, now I hope that is clear at this point. All right, here we have the third example. A particle of mass 5 kg is traveling along a smooth horizontal surface with a velocity of 15 meter per second. Given that a force, an external force applied to the particle over 4 seconds reduces the velocity by 8 meter per second, and that particle will still travel in the same direction. Now the task here is we need to find out what is the magnitude of the external force acting on the particle itself. All right. Now before you start, we are going to do a bit of visualization here. All right. Now let's look at how the behavior of the particle due to the introductions of the forces. All right. So let's see. Okay. Now initially it's traveling at 50 meter per second, acted by a force, and then its velocity reduces by 8 meter per second there. Right. Now as usual, before we start, we're going to write down all the information that are given to us. So in this case, we have the mass, which is given as 5 kg. Okay, what other information is given? We have the initial velocity, 15 meter per second, and then we have the final velocity. It was stated that the velocity was reduced by 8 meter per second. Therefore, okay, I think I used the wrong symbol here. Not really wrong, but I try to differentiate between the initial velocity and its final velocity. So its initial velocity was 15 meter per second, reduced by 8 meter per second. So it was reduced by 8 meter per second, meaning that it is reduced by 8 meter per second in such a way. Therefore, the final velocity due to the introductions of the external force is 7 meter per second here. All right. Now, by using the same principle, impulse, which is given by J here, it can be written as the product of force and time, or it can be represented as change in momentum. All right, now there you have it. Now the force itself, initially, if you have no idea which direction the force is acting, that is fine. But if you look at the simulation itself, in order to reduce the velocity by 8, right, the force must be acting in the opposite direction of the motion itself. Okay, so let's assume that we don't really know the direction. So therefore, we'll write down F in this case. Acted, yeah, there's one more information I forgot to label here, which is 4 seconds. So acted on for 4 seconds. We have the mass, which is 5. And then our final velocity has been reduced by 8 meter per second to become 7 in this case. And then our initial was 15 here. All right. Now, therefore, in this case, we have 4F equal to negative 40 here. Therefore, we find out that the external force that is acting on the particle must be acting in the opposite direction, because this negative sign here shows the directions of where the force is acting on the object. It has a magnitude of 10 Newton here. All right, now I hope that is clear. Stay tuned for the next section. All right, next we're going to continue on with the next objective. Previously, we have managed or successfully recap impulse and its momentum. Now we're going to further proceed on with the second second objective, or the second and third objective. For this second objective, we are going to introduce a new law or new equations or theory that we're going to use for any situations that involve a collision in this case, right? Now, this law is known as Newton's experimental law or Newton restitution's law. And then for the in the context of the syllabus itself for 9231, the value of coefficient of restitution, which is the E, would always fall within that domain 0 and 1. Of course, in reality, the coefficient of restitutions could be more than 1, right? Just for your extra knowledge, right? And then later on, we're going to look at example of collisions that is considered as perfectly elastic, where it would produce a coefficient of restitution equal to 1. And then lastly, we look at one example maybe that involve a perfectly inelastic, where the coefficient of restitution is equal to 0. Right? We will present either one of these, right? And then lastly, this is I will put it as the second part of my video, into my second part of my video, how to actually apply conservations of momentum and both the Newton's restitutions law to analyze any collisions in both rigid body. And then my second part of this momentum, I will leave it to the oblique collision, where it involves a rigid body. All right, I hope that's clear. Okay, let's look at the next part. I'm going to introduce to you both. There are two more concepts: the conservation of momentum, which some of you have already picked that up in physics, and then I'm going to introduce to you what is known as Newton restitution's law, or Newton's experimental law. Okay, conservations of momentum. All right. Now, conservation of momentum is there's a very strict definitions that we need to follow if you really want to apply this theory correctly. Uh, Now, first of all, you have to make sure that your analysis involve an isolated system, like the system of consideration only involved in that particular domain, where there is no external force that is actually acting on the object that involved in the collision. That is called the isolated system, or in a closed system where we don't consider external force acting on the object during collision. Because there's no external force acting on the object during the collision itself, therefore, we know that the resultant force must be equal to zero. Using Newton's second law, rates of change in momentum should also be equal to zero. Yep. And then by using that, we will be able to derive the formula that we always use all this while, which is known as the um, conservation of momentum. All right? We can write the conservations of momentum in a more explicit form by saying that um, the total momentum before any collision must be the same as the total momentum after collision. Or simply put, the total momentum for any object involved in the collision in a closed system would always remain constant. For a mathematical analysis, we prefer to use total momentum before must be the same as total momentum after. But in physics, they will say that in a closed system, the total momentum uh, for the for any collision involved in a closed system would remain constant. So the constant part basically means the total momentum before after must be the same. Right? So, and then if you like to visualize how the equation look like, usually we prefer to write m1u1. U is a standard unit that we use to represent initial velocity, whereby v we use it to represent the velocity after collision. Or you can write it in the summation form, or in a more simplified form. Okay, all right. Now next we're going to look at how we're going to apply this. Right, now let's look at our first example. Perfectly elastic. We try to understand these questions, then you can get a better idea or picture of what is known as perfectly elastic. Right? The problem that we have here would be two particles P and Q. You can see that from the diagrams on the right. Traveling on a smooth horizontal plane, P has a mass of 3 kg and Q has a mass of 1 kg. P has or P was moving at a velocity of 3u, and then Q is moving at a velocity of u, which mean indirectly P is moving faster than Q then. So therefore, there's highly likely P would collide with Q in this case, such that the collision is perfectly elastic. Now we need to find out the velocity of each of the particle after the collision. And then lastly, we're going to confirm that the kinetic energy is the same before and after collisions here. All right, so I hope that is clear. All right, let's look at what do we expect to see generally. All right, so in this case, you can see that this is before collision. So you can see that moving faster. It's going to collide. The P is going to collide with the Q for sure. And then after collisions, there will be impulse. As we know, uh, the moment impulse involved, there will be change in velocity. Yeah. So let's look at what happened next after collision. So after they have after P collide with Q, both of them change velocity. So in this case, I'm going to label their velocity as v1 and v2. Okay, and then after their velocity changes, they could be moving in any directions. Okay, it could be moving in the same direction, or maybe one could actually rebound. We are not sure, but we can find out from the conservations of momentum. shortly. All right. Okay. Now let me show it to you what happened after this. You can see that after they collide, they will move with a different velocity after this. Okay. Now let's apply conservations of momentum in this case. We know that total momentum before must be the same as total momentum after here. Okay. Now in this case, the u1 that we are using in this case is initial velocity for p, which is 3u, and then initial velocity for q is u in this case. The mass is p for mass is 3 kg. The mass for q is 1 kg. All right. So the same thing, we are going to find out what is the velocity after the impact itself. Okay, let's apply the conservation of momentum by using conservation of momentum. All right, through the conservation of momentum, the total momentum before collision, this part here, total momentum before collision, you can write down the formula if you're afraid that you might have forgotten the formula itself. Here you don't really need to include the vector notation because it's still sort of in one direction. Yeah, and then we do consider them as a particle at this point of time. And then bear in mind direction is very important. I need to stress that direction is very important. So we assume that going in this direction is considered as positive for all the vector quantity. Now we're going to plug in all the informations that we have. We have 3. This is 3u plus a 1, I think. Yeah, the other one is u. And then the same go for this 3v1 plus v2. And then we can simplify this a bit. We will get 10u. All right. And then I can label this as my first equation, maybe. All right. Okay. And then in this context also, it was mentioned that this collision is perfectly elastic. Now, perfectly elastic is defined as where the collision involved, uh, and then after the collision itself, the total kinetic energy is conserved, which means total kinetic energy before collision and total kinetic energy after collisions remain constant. All right, now we're going to use that concept using conservations of kinetic energy. So, second part, using conservation of kinetic energy. All right. Now, the total kinetic energy before collision was given as such. Okay, write down all the formula first. Okay, now this is only true. Um, kinetic energy is conserved only when it is perfectly elastic. collision in this case. Right? And then for simplifications of analysis here, we can just cross out all the half there. Just fill in the mass, and then this is 3u square. Don't forget the square is very important. This is u square, that is fine. And then we have 3v1 square plus v2 square. Okay, that's what we have. And then we're going to rearrange this correctly. So for instance, in this case, we can rewrite as 3v1 square plus v2 square equal to, we have, what do we have here? 27, 20, 28 u square. All right. Now, of course, solving this should not be a problem here. You can always use substitutions and so on and so forth here, right? So in this case, if I'm using substitutions, for instance, I would have or obtain my 3v1 square, and then this would be my, what do I have here? 10u minus 3v1 square. Okay, that will give me 28 u square. Okay, and then from here itself, I will get 12 v1 square, and then what we have here would be minus 60 u v1, and then finally I will have plus 100 u square. So 100 u square is basically 72 u square equal to 0 here. And then of course you can simplify this. I noticed that I can divide that by 12, so that would give me u. Okay, and then there you have it at this point. Okay, now from here you can find out the answer easily. Okay, now I'm going to pause here for a while for you to look at all the informations that we have obtained so far, and then next I'm going to continue on from where we left out, and then solve for the velocity v1, and then thereafter we can obtain the velocity v2, right? So stay tuned. All right, as I mentioned before we are going to attempt the previous question using Newton restitution's law. I'm going to walk you through a very simple idea behind how this Newton restitution's equations was derived from. Okay, now we're going to revisit the same collisions again. Okay, now we state that there are two particles collide with each other. Okay, one of them is moving at a velocity of u1, for instance, and the other one is u2. So I'm not sure which one is faster than which, but most probably U1 will be faster than U2 in this case for them to be able to collide. So after they collide, after the collision itself, yes, they will change velocity due to the impact itself or the impulse. Right. Therefore, we will label that as V1, V2 for um, generalizations here. Okay, and then let's assume that this is a perfectly elastic collision. Okay, I'm going to show you how that Newton restitution's formula was derived, and then some of the focus on the formula that we need to pay attention to. All right. Okay. Now, by using, we need to apply these two concepts to derive that Newton's restitution's law, right? For perfectly elastic um, condition. Okay, bear in mind we are looking at a perfectly elastic collision. Here, I just write it down for reference. So perfectly elastic collision. Um, the first uh, the first principle we're going to apply is conservation of momentum. We have written that down previously. So here I just rewrite again. Okay, there will be okay. Um, Now, before we proceed further, I'm going to rearrange these equations here so that I can collect the like term with respect to their masses. All right? Therefore, I would have something like this, for instance. Um, I would say m1 u1 minus v1, for instance, and then whereby m2. Okay, now I'll label this as my first equation here. Okay. Now next, knowing that this is perfectly elastic, I will apply my conservations of kinetic energy here. Therefore, okay. And then doing a bit of simplifications and then grouping with respect to their masses. So I will get, okay. And then there you have it. You can see we have set up two simultaneous equation. And then from here, we can solve it through this operation here. We're going to take 2 divided by 1. Therefore, we will have u1. Okay. Now, by making assumptions that u1, okay, we are using that assumption saying that u1 should not be equal to v1, and then at the same time, u2 should not be equal to v2. In any kind of collisions, I believe, okay, I might be wrong. Most of the time, uh, there will be a change in velocity. That's what I would like to believe here, all right? So from here, we can simplify this fraction. Knowing that that is true, therefore this can be simplified. You can factorize this properly. Therefore, you will end up with this. And then doing a bit of arranging here. So take for instance, I will have u1. All right, and then just to restructure that. mm, okay, now it's very important to have this ratio. This ratio is what we known as the coefficient. This is known as the coefficient of restitution. E. And then for any perfectly elastic collision, the coefficient of restitution is equal to 1 here. And then by definitions now, by definition, the coefficient of restitutions as defined by Newton is given as a uh, relative velocity of separation. You can see that this is a relative velocity of separation over relative velocity of approach. Relative velocity of approach. This part is separate. Separate means after. So refer to after collisions that were separate. Okay. We take the difference between their velocity after collision. The choice of difference here is basically up to you. If you want to take V2 minus V1, also can. That is also correct. If you want to take V2 minus V1, also correct, right? Whereas um, the second sections, the denominator represent the relative velocity of approach. This basically refer to before the collisions, when they get closer and closer before the collision itself. So this is relative velocity of approach. Um, you can also take u1 minus u2 or u2 minus u1 here. But um, a word of precautions here is uh, if you like this formula, you can always take it as a relative velocity of separation divided by relative velocity of approach. But the one minor detail that you need to pay attention to is, okay, if you take V2 minus V1, which means if you take this one, subtract off with this, then therefore your denominator, you should follow the order of u1 subtract with u2, so that we can get the coefficient of restitutions correctly. So here I'm going to write down just for you to remember. The coefficients of restitution is given by v2 minus v1, u1 minus u2, or you can write down as v1 minus v2, u2 minus u1. That's what I mean. Now, in terms of magnitude itself, if you want to put a modular sign to this ratio, yes, it has a fixed magnitude. Doesn't matter what value they are looking at, right? But I want you to remember it must be a relative velocity, not relative speed. Of course, some books use relative speed because they apply the magnitude of the coefficients of restitutions. For me, I always prefer to follow this closely so that I will be able to obtain the velocity after collisions. May it be in the same directions after collision, or maybe one of them will change direction. Yeah. So that's the importance of making sure the order of your ratio is correctly written. So please pay attention to these Newton restitutions. Okay. All right. So I hope that's clear. I'm going to go back to the previous question and then solve it using Newton restitutions law, and then after that verify the conservations of kinetic energy. All right, let's look at the same questions again in this case, but this time we're going to apply the Newton restitutions law. Okay, just let me show you again the collision. Okay. So before collisions, we have P is moving faster at 3u, moving towards Q, and then they collide. And then after the collision, okay, both of them change direction. Sorry, not both of them change direction, both of them change their velocity. The velocity changes. Okay, here I'm just making assumptions they would be moving in the same direction based on your mass and their velocity. Okay. Now from here, I'm going to apply Newton restitutions law together with conservations of momentum. Now, conservation of momentum, again, I'm going to write down in short form now, COM. Okay, that is basically, I'm going to write down the mass directly. So that is 3U plus 1 kg, and then U is equal to 3V1 plus V2. Okay, and then from here, we have 3V1 plus V2 is equal to 10U. Basically, that's what we obtained previously. Okay, now next we're going to apply the Newton restitution law. Newton restitution law. Okay, now by using Newton restitution law, we're going to use the relative velocity of separation. Okay, now that depends on what you want to use here. I'm going to write down the formula one more time. Coefficients of restitution is given by, usually I prefer to write V2 minus V1, and then I will change my denominator U1 minus U2. Okay, so please pay attention to this part here. All right, and then knowing that this is a perfectly elastic collisions, oh yeah, one more thing, we must remember that in your syllabus, the coefficient of restitutions satisfy this domain 0 and 1. Okay, for perfectly elastic, collision, we know that E is equal to a 1 here. Right. Now, because E is equal to a 1 here, therefore, we indirectly obtain this. We can get V2 minus V1 divided by U1. This is U1. U1 is actually equal to 3U. U2 is equal to U here. So you take equal to 1 here. Therefore, we indirectly form our second equation, V2 minus V1 equal to 2U. Now, that will be our second equation. So solving this using Newton restitution's law is much more less risky, I would say, because it involves linear simultaneous equation here. Okay, so we can solve this quite easily just by taking one, using elimination method. So taking 1 subtract off with 2. Therefore, I will have 4V1 here. That will be a 8U. That simply means V1 is equal to 2U. So V1 reduces its velocity. And then from the same equation itself, my V2 will be 2U. I'm using this one here. So 2U plus a V1. And then yes, it does matches with our previous answer there. All right, but bear in mind I have not finished solving this. I need to verify whether their kinetic energy is conserved or not. Therefore, their total kinetic energy before collision, so I will say kinetic energy before is given by half m, is it m? Yeah, correct, 3 and then there's u square, and then that's generally give us 27 over 2, 14 u square. So the total kinetic energy before collision is 14 u square. So now I'm going to calculate total kinetic energy after collision. So after collisions, this become 2u now, and then this one become 4u. Alright, so therefore I'm going to plug that in. And then let's see what do we have here. We have 6 here. We have 8. This one is 8. This one is 6. So 14u square joule. Right. Now, therefore, we have successfully verified that your kinetic energy is conserved in a perfectly elastic collision using Newton restitution's formula. All right. Now, I hope that's clear. All right. Let's look at 2 examples just to exercise the new Newton restitution's law formula. All right. Okay. Now let's look at the first example here. We have 2 smooth spheres of equal radius resting on a smooth surface. Sphere A has mass 2m and sphere B has a mass 3m. Now the coefficient of restitutions between the spheres is 2/3. Sphere A is projected towards B with the velocity 2u, and sphere B is projected towards A with the velocity u. So sort of the particles are moving towards each other. Now we need to find out the velocity of each of the sphere after the collision. We also need to find out their loss in kinetic energy. So let's take a look at how the collisions look like. Okay, let's look at how the simulation look like in this case. Okay, we can start off by looking at before collision. Right, so both of them moved towards each other, they collided, and then thereafter, after collisions, there are many possibilities. I'm just showing you one of the possibility here. You can see that after they collide, they could be moving in the same direction, or one of them could change direction and so on. Right? So let's find out from the Newton restitution's law here. Okay. Right, now we are going to apply both the conservations of momentum and restitution's law in this case. So we're going to start off from the conservation of momentum. Conservation of momentum in this case would give us, we have here as 2m. Okay, and then we have this part here as 3m. Is it 3m? Yep. And then the initial velocity was here, given here. All right. So by using conservations of momentum, I'm going to write it down C or M here. So we can write down that as projected with 2u, so that is 2m. Okay, again, don't forget whenever you apply conservation of momentum, we make assumptions this direction is considered as positive. The same for after collision, right? And then now because both of them move towards each other, okay, so therefore the other one will be, we have to pay attention to the second motion here. So we have 3m, but it's moving in the opposite directions of u. So therefore that is a negative u here. So that's the only thing you have to be very careful of. And then after the collisions, basically I have no idea how they would behave after collisions. So in this case, I'll just write down as it's possible that doesn't matter where or how they behave, you can just write down this as 3m and then v2. Okay, and then leave it as it is. All right, now of course we need to simplify this. We have a 4 and a negative 12, so negative 8 here. We will have 2v1 plus 3v2 equal to negative 8. Yep, that will be our first equation. All right. By using Newton restitution's law, okay, by using Newton restitution's law, here I'm going to take v2 minus v1 over u1 minus u2. And then the coefficient of restitution is actually given for us, which is 2 over 3 here. Okay. And then from here we can form another linear equation. Our u1, this is our u1. Our u2 is here. Okay. Now bear in mind u1, I better write it down here. u1 is 2u, yes, correct. It's in the same direction as our reference, but our u2, the only thing you have to be very careful of is u2 is negative u. It's moving in the opposite directions of our reference here. Okay, so therefore if I substitute this one inside here, I would have 3u actually. Therefore v2 minus v1 is equal divided by 3u equal to 2 over 3. Alright, now from here it's very obvious, v2 minus v1 is equal to 2u. Okay, oh yeah, I think I missed out. This is not negative 8. I think I accidentally look at this as a 4. Alright, please forgive me on that. You can also fix that on your own. Oops, sorry, hold on. From here, right, there is actually a u. So we have actually negative 3u, and then we have negative 4mu actually. Now for that, we will have just mu. Okay, so just let me correct this. Okay, so did I get it right? Okay, just let me correct that. That is negative u. Yep. So this is not 4, is u. So negative 3u. This is 4u. So therefore, we have a u here. Okay. So there's a u. And then here we have 2u. That will be our second equation. And then all we need to do is just solve this simultaneously. Now, if you want, you can multiply 2 onto here. So if you multiply 2 onto here, you will get a 2 v2 here, 2 v1, which is a 4u. Yeah, maybe I will label this as 3 in this case if you want. Okay, so from here onwards, all we need to do is just eliminate the equations by taking 1 plus 3 in this case. So if I take 1 plus 3 here, I will get a 5v2. That is actually a 5u. And then eventually I will get v2 equal to a u. Right. Now if v2 is a u, then v1 must be v2 is a u, then v1 must be a negative u. Right. So you can see that one of the particle does change direction, so it actually moves in the opposite direction. As you can see, the Newton restitution's law will help us to determine what will happen or how would the particle behave after the collisions. Now we have successfully obtained our v1. I'm going to write it down here. So v1 is equal to negative u, which means it's supposed to move in this direction. And then v2, yes, V2 is correct, it's moving in this direction. All right. And then lastly, we're going to determine if there is any kinetic energy loss or not. Okay, so just let me clean this up. Then we are ready to determine. All right. Now, in order to determine the loss of kinetic energy, we're going to determine the change in kinetic energy. So change in kinetic energy will be the final kinetic energy subtract off with the initial kinetic energy. All right. So our final kinetic energy will be here. That will be 2m negative u square we have 3m and then also moving at u square here. Right now that will be our final kinetic energy. We're going to take the difference between the final kinetic energy and its initial. Writing down this way is easier. We can check side by side the mass. The initial was 2u. Then this one is just actually it doesn't matter because it's a speed here. Speed we don't really need to take into account its direction. Okay. Now from here you have mu. This part is mu square. This is 1.5 mu square. So therefore you get 2.5 mu square. So therefore 2 over 5 mu square. Subtract off with what do we have here? We have 4 mu square here. You have 4.5 here. So this is 4, 9 over 4. This is 4. Let me see. Did I get it right or not? This is a 4, 8, 11. So 11 over 2. Therefore 11 over 2 m u square. Okay, just let me check properly. Sometimes I'm a bit lost with my calculation, right? Please forgive me on that. You have 4, 8, 11. Yeah, should be correct. So from here, I will be able to get a negative 3 mu square. Okay, now the negative sign actually indicate there's a loss in kinetic energy. Therefore, finally, we are going to write down loss of kinetic energy is about 3 mu square joule. All right, now I hope that is clear for this question here. Let's look at our last example for today before we proceed on to the part 2 of this momentum. All right. Now we have two smooth spheres of equal radius resting on a smooth surface. We have a sphere P has a mass m, and then sphere Q has a mass of 2m in this case. Now the coefficient of restitutions between the spheres is E. Sphere P is projected towards Q, which is stationary at a velocity u. We need to find the conditions on the coefficient of restitutions such that the P's direction is changed. Okay, let's look at how does the particle behave first before we start here. Okay, now let me show you how it look like. So you can see that P move towards Q is going to collide with Q. That is before collision, and then after collisions the directions of P changes, so it will look something like this. Both of them will be moving in the designated direction. Okay, now for this, we're going to label all the informations correctly. So M1 is 2M, and then M2, did I get it right? Okay, the first one is M. I think I wrote down wrongly. So this one is M. The second one is 2M. So this one is M, this one is 2M. Yep. Okay. And then projected at the speed of u, at the velocity of u here. Alright. And then we are ready. The other thing you must remind yourself whenever you attempt collisions questions, you must assign the directions, your reference. So we put a reference, this direction is positive. Therefore, we're going to apply conservations of momentum as usual. So for conservation of momentum, we have mu, I think, because that's the only one that is moving. That is before collision, must be the same as the momentum, total momentum after the collisions here. Alright, so here we have m also. Okay, I can actually write down v1 here if you're not sure which direction it is that, and then after that I will have 2m v2. Okay, right, and then there you have it. And then by simplifying this, you will get 2 v2 equal to a u. Now that will be our first equation. Okay, and then next we're going to apply the Newton restitution's law. Okay, using Newton restitution's law, I'm going to use v2 minus v1 as usual, divided by u1 minus u2 is equal to the restitutions E. Okay, so from here I notice that u2 is 0, my u1 is u, therefore I can arrange this as v2 v1 equal to EU. Okay, now bear in mind here I would like to advise my students, knowing that these simulations here is the actual realistic conditions that we expect the collisions to behave. But mathematically, we have no idea initially before we reach the conclusions whether they are going to change direction or not. Right? So therefore, that's the reason why we still put it as addition. Here, I did not put negative or positive onto my V1 here. Right? So from here, I can solve this quite easily by taking 1 with 2. Okay, so solving this, I will get 3 V2. 3 V2 would be equal to, if I add up, let me see. Yep, correct. So that is 1 plus E U here. From here, I will get V2 equal to 1 plus E over 3 U. Okay, now that's my V2, and then of course from here I will be able to obtain my V1 quite easily. That would be, let me see, what do I have here? I will have 1 plus E 3 minus E here U. Yes, okay. So from here, I would end up with the, let me see here, what do I have? I get 1 minus 2e over 3 u. Let me see whether I got it correct. Yep, okay. And then from our simulation just now, we know that P changes direction. Changes directions means V1 must be less than 0 because we assume this direction is positive, that direction must be negative there. Because it's less than 0, that simply mean 1 minus 2 E over 3 U must be less than a 0. Okay, if you arrange it properly, your E will be greater than a half. Right. Now that will be the conditions for the coefficient of restitution for P to be able to change direction, for instance. Right. So I hope that give you a clear idea how to apply your conservation of momentum, Newton restitution's law. Right. So this is the first part of momentum. So take this time to go through all this, and then there will be a practice questions for you to get used to this before we move on to the last section, which is known as the oblique collision.